In this video, we're going to look at this example, this question from the CAS. Before you do that, I would really recommend you look at S2.1 from the Year 2 textbook, because these videos go through what does mutually exclusive mean, and it also goes through some of the basic set theory notation that I'm going to use. So we need to understand what mutually exclusive means first. So here we've got two events that are mutually exclusive. So A and B are mutually exclusive. And what this means is that there's no overlap between A and B. Or another way of saying that is that A and B can't happen at the same time. So the probability of being in the intersection where A and B happens is 0. Well, these two sets, A and B, are not mutually exclusive. The events A and B can happen at the same time with that probability. But it turns out that these two events are actually independent. So let's look at what independence of two events means. Well, the definition of independence is that the probability of A and B happening is equal to the probability of A times by the probability of B. Well, let's check whether this works. So here we've got probability of A times probability of B is equal to probability of A happening is everything, all the probability within the A circle, which is 0.1, multiplied by all the probability within the B circle, which is 0.2. And if you times them together, you get 0.02. And that is equal to the intersection, the probability that both of them happen at the same time. So that is equal to probability of A and B happening. So that means that they are independent, and that's our definition. And in the videos in chapter 2, you'll see why this definition makes sense. So let's have a look at the question now then. So we're asked for the two events that are mutually exclusive. So this is the two events that don't overlap, where the two events can't happen at the same time. Well, it's clear that the event A and S are mutually exclusive. So A and S are mutually exclusive because the probability of both of them happening at the same time is 0 because they don't overlap. In part B, we're going to have to do a bit of problem solving to find out what R is. So first, let's try and find out what Q and P are, because we're going to have to use that to find out R. So we're told that the probability that Sergey is late for school is 0.2. That means the total probability within the S circle has to add up to 0.2. So we can see that that must be 0.15. And this probability 0.2 is split into two regions. There's a probability of 0.15 that only Sergey is late and Dawn's not late. And there's a 0.05 probability that Dawn is late and Sergey is late in the intersection of the two that overlap. Next, we can find out what the probability of P is, which is just Aliona being late. Well, we're told that A and D are independent. So recall that the definition of A and D being independent is that the probability of A and D happening at the same time is equal to the probability of A happening multiplied by the probability of D happening. Well, the probability of A and D happening is this part here, this region, which is 0.1, the overlap of the two circles. The probability of A happening is the sum of all the probabilities within the A circle. So we've got that probability P plus 0.1. And we're going to multiply that by the probability of D happening, probability of Dawn being late. And the probability of Dawn being late is all three of these probabilities added up. So that's 0.25. So if we solve that, we're going to get P plus 0.1 is equal to 0.1 divided by 0.25, which is 0.4. So we get that P is equal to 0.3. So let's put that in. And that's the probability that only Aliona is late and no one else. Now we're asked to find the value of R. Well, we're going to use the fact that if you add up all of the regions in a Venn diagram, you get 1 because probabilities sum to 1. our total sample space is 1. So we're just going to do 1, subtract all the other probabilities in the Venn diagram. And if we do that, we get R equals 0.3. And then in part C, we're asked to state whether D and S are independent, giving a reason for your answer. So remember, if they're independent, then we know that the probability of D and S happening at the same time, so both Dawn and Sergey are late, is it equal to the probability of Dawn being late times by the probability of Sergey being late? Well, let's check whether that works or not. So the probability of Dawn being late times by the probability of Sergey being late is, well, the probability of Dawn being late is the sum of the probabilities within the Dawn circle, which is 0.25. And the probability of Sergey being late is 0.2 inside the Sergey circle. And if we times those two things together, we get 0.05. And because that is equal to the probability of both Dawn and Sergey being late, because that's the intersection of the two, 0.05, then that means that they are independent. So D and S are independent, because that is equal to the probability of both Dawn and Sergey being late. Right, in part D, the school teacher thinks that if Dawn is late, if Sergey is late, then Dawn tends to be late too. And we're asked to comment on that belief. Well, because we know that D and S are independent, this means that basically, if Sergey is late, it doesn't change the probability that Dawn is late. So the probability that Dawn is late is not going to depend on whether Sergey is late or not. So the teacher is going to be incorrect. So we could say that because D and S are independent, the probability that Dawn is late does not change based on whether Sergey is late or not. So the teacher is incorrect. Well, that would be enough to get the mark in this question, but let's look at this in a little bit more detail. So the teacher thinks that the probability that Dawn is late, given that Sergey is late, so let's write this down, probability that Dawn is late, given that Sergey is late, the teacher thinks that this probability is higher than just the probability of Dawn being late. Now, if you don't recognize this notation, you'll have to go and watch these videos in chapter 2 before you understand what I'm going to do here. So let's try and prove that this is not true based on what we know about independent events. What we want to try and show actually is that this probability on the left, the probability of Dawn being late given that Sergey is late, is actually equal to the probability of Dawn being late. So this is what the teacher thinks. So actually we know that the probability of, so this is what's actually true. We know that the probability of Dawn being late given that Sergey is late is equal to the probability of Dawn and Sergey being late divided by the probability of Sergey being late. That's our formula that we've learnt in chapter 2 for conditional probability. Now, because we know D and S are independent, we know that the probability of Dawn being late times by the probability of Sergey being late, that numerator, those numerators are the same because of independence. Okay? And we've still got probability of S on the bottom. So we can cancel those probabilities and we just end up with the probability of Dawn being late. So this means that the probability of Dawn being late when we know Sergey is going to be late, is just exactly the same as the probability of Dawn being late. So we know that Sergey being late does not change the probability of Dawn being wrong. So we know that this assertion that the teacher is saying is wrong.